Yeah. So also, can you guys confirm if my, audio is fine? Like, are you able to hear me properly, or is the audio very low? How is it? Okay. Okay. Fine. 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 So yeah, we will also be discussing something known as bipartite graphs, right? And let me also write this application of traversals, right? So today's class will be like very, very basic. We'll also look at this thing known as, how do you take in, or, how do you represent graphs? Okay, give me a minute. Yeah, sorry for the delay. So we'll also look at, representation of graphs. What are the various ways of representing graphs? And there is one unique way, which I'll tell you, which is known as an adjacency list of sets. So you must have seen this. I mean, for people who are already comfortable with graphs, you must have seen this thing known as, adjacency matrix and adjacency list. So when you talk about adjacency list, people usually, do like a 2D, I mean, like a 1D, how do I put it, 1D array of lists, right? So what we'll also look at is a 1D array of sets, right? Or a 1D array of maps, for example, something like this, which is very, very useful in certain problems. And I mean, a lot of people don't know about that. So somebody saying, please discuss also the application of bipartite graphs. I also watched it. See, there is no application as such. It is just that once you have the idea clear in your mind, then you can think about problems related to graphs based on bipartite graphs. Like if you don't understand what are bipartite graphs, then it doesn't make sense to basically when you use it as an application, right? But if you understand what are bipartite graphs, sometimes you might be able to use it in certain problems, like just the idea, right? Okay. So this is all that we'll be discussing today. In case this seems redundant for you, then don't attend the class. Preferably complete the pending daily tasks that you have, right? Okay, so now let's start with the terminology a bit, and let's start with types of graphs. So the first type of graph, okay, this is how it's going to look like. Let's see if we can do something else. Okay. Is that where to keep this itself? Okay, I don't think this is going to work. So let's just keep this, right? So let's start with types of graphs. The first type of graph, I mean, the first basic demarcation is undirected versus directed, right? So let's see what are undirected graphs and what are directed graphs. So for example, if I draw something like this, right? And again, I think before that, it would be better if we discuss the terminology, right? So let's first of all discuss this part, these things, and then we can get into the types of graphs. So first of all, let's try to understand what exactly is a graph. Okay, so a graph is nothing but a collection of nodes connected through edges. So if you look at something like this, this is a graph. Okay, all of these circles that I've drawn are known as vertices. These are known as vertices. All of the connections that you have, like these yellow connections, all of these are edges. You also call the vertices as nodes, right? And now if you look at it, there is also this concept of a neighbor. What is a neighbor? Can anybody guess what is a neighbor? For example, if let's say I look at this node and let's number these nodes, something like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Can you tell me what are the neighbors of node 8? See, all these circles that I've drawn are nodes. All of the connections that you have are edges. Fine. So can you tell me what are the neighbors of node 8? The neighbors are basically all those nodes which you can reach by just through one edge. For example, if you look at this node 8, what are the other nodes that this 8 can reach with just one edge? So if you look at just one edge, you can reach here, which is node 9. If you look at one edge, you can reach here. Look at one edge, you can reach here, right? So these are the neighbors of node 8. So the neighbors of node 8 are, let's put it like this. And also this is like a representation, okay? When I write n of 8, this is the meaning of neighbors of 8, right? So neighbors of 8 are what? 4, 9, 6, right? Similarly, can you tell me what are the neighbors of node 4? Tell me what are neighbors of node 4? The neighbors are, see, 8 obviously, because you can reach 8 by just one edge. 5 is a neighbor, 3 is a neighbor, and 2 is a neighbor. Okay, so the neighbors of 4 are 2, 3, 5, and 8. Right, so you all understand what are edges, what are vertices, what are nodes, and what are neighbors, right? So, and another thing here is that these neighbors are also known as adjacent vertices. Let me put it like this. Okay, these neighbors are also known as adjacent vertices. We know what are vertices, we know what are edges, we've looked at what are neighbors. Now let's talk about what is the degree. Okay, so can anybody make a guess what do you mean by degree? The degree is very simple. The degree means the number of neighbors of any node. Okay, so degree is number of neighbors. Okay, so this neighbor thing is also represented like, this is also represented as n of x. When I write n of x, it means all the neighbors of a node x, right? So similarly, the degree, basically, let's put it like this. Number of neighbors, and the degree is basically, let's put it like this, degree of x is equal to the number of neighbors. Okay, all right, degree of x is basically the number of number of neighbors of any node. So can you tell me what is the degree of node 2? Here in this example, what is the, I hope my screen is visible. First of all, like everything is clearly visible, right? Like even if I do it like this, is that visible to you, or is it too small? Like I hope this is fine, right? So if you look at the degree of node 2, degree of node 2, what is the degree of node 2 here? How many neighbors does 2 have? 2 has 3 neighbors, right? So degree of node 2 is 3. Degree of, let's talk about node 8. What is the degree of node 8? This node 8, again 3, right? Similarly, what is the degree of node, for example, 11? What is the degree of node 11? Tell me. 2. Simple. Okay. So we understand what are neighbors, we understand what is a degree, and we understand, vertices, we understand edges. Now let's talk about this concept of a self loop. So what happens is that, you might see a graph like this, right? This is a normal graph, but if I do something like this, that, between two, on a single node, if I add another edge which goes from that node to the same node, right? Basically, this green node is there. Instead of having an edge to other nodes in the graph, it has an edge which, is corresponding to itself. So this is known as a self loop. Okay, there is nothing much to explain here. Like, this graph, if you look at it, this graph doesn't have a self loop. If you look at this graph doesn't have a self loop. But if you look at this graph like this has a self loop. Okay, we can write it here. Fine. So self loop is covered. There is nothing really interesting about it, but they're just in order to, cover this entirely. That's why we are doing it. Now let's talk about this very important, concept of path versus walk versus cycle. Fine. So let's make a graph. Let's say this is a graph. Okay. Somebody saying multiple edges. Aman, what do you mean by multiple edges here? Multiple edges. See, this is not a self loop. If you have something like this, and if you add another edge like this is not a self loop. Okay, this is a multiple edge. There are 2 edges between the same 2 nodes, but this is not a self loop. A self loop is very self-explanatory. It is an edge on yourself. Okay, so this is not a self loop. Now let's look at this graph, and I'll tell you 3 examples, and I'll tell you what are these examples. Okay, so for example, if you start from node 1, and if you want to, like, let's number these nodes 1, 2, 3, 4, 5, 6, 7, 8, and 9. If you want to go from 1 to 7, for example, and let's say you take this path, okay? Let's say you take this path. You go from here, then you go from, basically you start from here, you go here, then you go here, then you go here, and then you go here. Okay. If you look at this path starting from 1 and going all the way to 7, can you see that every node is only encountered once? Can I say this? That every node in this path is only encountered once. I'm not revisiting a node here. I'm just going from 1 to 7, but I'm not revisiting any node. Can I say that? If I don't revisit any of the nodes, basically going from a node to some other node, if I don't revisit any node, this is known as a path. Okay, very simple definition. A path is basically going from one node to the other node to some other node without revisiting any of the nodes. That is known as a that is as simple as a path. Okay, this is a path. Now let's consider another example. Let's say you go from 2 to 9, you go from 9 to 8, you go from 8 to 7, you go from 7 to 6, you go from 6 to 4, and then from 4 to 2. What is this? This is a cycle. Going from one node and coming back to the same node. This is known as a cycle. Okay, does that make sense? Very, very simple. See, path is like going from one node to the other node without revisiting any of the other nodes. Right? And a cycle is as simple as coming back to yourself. Now, there is also this concept of, revisiting some node. For example, if you do something like this, you go here, you go here, then 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 you go here, and then you come here. This is not a normal path. Is this a path or not? I have visited one of the nodes twice. I have visited node 2 twice. So this is not a path, but this is known as a walk. Are you able to understand what I'm saying? Path versus walk versus cycle. Okay. Like if I were to, do a quick example, let's copy this and let's try to. Let's paste it. Okay, these are the three, let's say, graphs. Let's consider the paths, the cycle, and the walk. So yeah, this going from here, sorry. This is a path. Let me put it again. This is a cycle. Going from one node and coming back to the same node. Okay, this is a cycle, and this is a walk. So basically what we're doing is this. We're going like this, okay? Here we did something like this. Okay, so this is a path, this is a cycle, and this is a walk. Is that clear to all of you? Somebody saying, is 1 to 1 a walk? Yes, 1 to 1 is also a walk. Very good, Swapnil. 1 to 1 is a walk. If you go from here to here, then you come back here, that's a walk. Yes. There is no restriction on revisiting any node, multiple times, or taking an edge multiple times. There is no restriction on that. So basically, this is also a walk. Okay. So I hope this concept is clear, right? Path versus cycle versus walk. Any questions on that? I'll come to this, Ritesh. But is this overall clear? What do I mean by path, cycle, and walk? This thing. Okay. Now I have some questions for you. Cycle contains only one loop. See, as long as you're visiting a node more than once, that's a cycle. Right? This is also basically a cycle only. Like I would see, let's try to put it like this. Let me give you some statements here. A walk might contain a cycle, right? This statement. A walk might contain a cycle. Every path is a walk. every cycle is a walk. Okay. So now if I were to, draw, let's say, a Venn diagram, it would look something like this. Like, let's say this is a walk, this is a path, and this is a cycle. Okay. So Swapnil, like you're saying, the cycle only contain one loop. Then if you were to have a graph like this, for example, if let's say this is a graph, and let's do something like this. Let's say this is a graph, right? If you tell me, is this a cycle, like coming from here, going here, then let's say going here, then going here, then going here, I would say no. Like going here, then going here, then going here, then going here, and going here. Is this a cycle? No, because this is not ending on the same node, right? This is not essentially a cycle, but this is a walk. A cycle is just like going from one node and coming back to it. This is a cycle. And in a cycle also, you don't visit a node more than once, except for that one starting node. Okay. So if you were to say, is this a cycle, like going from here, going from here, going from here, going from here, and then coming back here? No, this is not a cycle. This is like generally a walk. It contains cycles although. Does that make sense, Swapnil? A cycle is like just going from one node, coming back to the same node by following unique edges, unique nodes. But a walk can, go through any edge or any node multiple times. Let me put it here as well. Okay, let's, remove this part and let's write some results separately so that this becomes an important slide for you.
Like, sir, मान लो कोई T shape का बन रहा है तो वो क्या है? वो
T shape का?
हाँ जी.
जैसे T shape कैसे हुआ ये?
P.
ये?
P for cat. P.
Okay, P. Okay, I see. Something like this. ये?
हाँ जी, क्योंकि इसमें एक नोड तो हम विजिट कर ही नहीं सकते फिर से.
No, I don't understand. Which you starting from here? Are you saying here?
No,
or
from bottom.
Okay, from bottom. Okay.
Yes.
So you start from the bottom. You go here. Let's put it like this. You go here, then 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 you go here. Right? This is you're saying, is this a cycle or not?
Yes, this is my doubt.
As a convention, this contains a cycle, but this is not a cycle completely. Because see, in a cycle, you should have all the nodes participating and it should look like a complete cycle. Does this look like a complete cycle to you? Like it should look like a circle, exactly, like this. That's a cycle. But this is a walk. It contains a cycle. Now, does that make sense?
Okay, so
this is a cycle. This is a cycle.
Yeah, so it must have only like one circle.
Yeah, exactly.
Okay.
If you're doing two circles, if you're doing something like this, going from here, here, this is a walk. This is not a cycle.
Okay, I understand.
Okay. So see, I'll also write some results here. There is a path contains unique nodes. Okay. Unique nodes and edges. A cycle contains unique nodes and edges except the last node, except the first and the last node. Basically, because you start from one node and you end at that node, right? This is a cycle. A walk is any movement in the graph. It doesn't matter if you are coming to the same node again, if you're following the same edge again, it doesn't matter. It is like any movement in the graph, that is a walk. So now does that make sense to all of you? Like difference between walk, cycle, path? A walk is like, the big daddy here. It includes everything, the path and the cycle. And a cycle is basically a path only with just, both of its ends combined together, if you look at it. Walk always, see, no. A path is also a walk. A walk doesn't have to necessarily, see, this is what I'm saying. This is a walk, this is a Venn diagram here representing everything. A walk also includes a path. Any path is a walk. Any cycle is a walk. Any movement, in fact, in the graph is a walk. So does that make sense to all of you? Write a +1, anything in the chat if that makes sense to all of you. Is 1 to 1 a cycle? Where you're saying? See, like I said, no, 1-to-1 is not a cycle. 1-to-1 is not a cycle because it needs to contain unique nodes and edges. Is the edge from 1 to 2 unique in that? No, you're repeating it twice. So that's not a cycle exactly, that's a walk.
I don't understand. Like 1-to-1 is a like circle only, right?
No, but you're reusing an edge, right? Once you visit an edge, that cannot be reused. If you reuse an edge, then that's not a cycle.
Okay.
Like if you look at,
if there is a loop,
sorry, please go again. You go here, you use that edge,
there's a
right?
loop from
I am sorry, I think I'm not able to hear you. Is the voice cracking on everyone's end or only my end? Okay, all right. Yeah. So this is how it is, like, 1-to-1 is not a cycle because you are reusing an edge and a cycle cannot reuse an edge. Contains unique nodes and edges except the first and the last node. All right. So I hope this concept is clear. Path plus walk plus cycle. Cool. Let's now talk about this concept of simple graph. So a simple graph is, like as the name suggests, very simple. There are no complications in it. A simple graph is just this thing. Okay, let's remove this. Let's talk about what is a simple graph. So a simple graph is any graph which doesn't contain self loops and multiple edges. Okay, self loops you all understand. Let me show you what is a multi-edge, multiple edge. So if you have a graph like this, if let's say this is a graph, if I add another edge, let's say these are the nodes 1, 2, 3, and 4. If I add another edge from 2 to 4, this is a multi-edge, multiple edge. Okay. And similarly, like this is a self loop. So a simple graph is a graph which doesn't contain a self loop and which doesn't contain a multiple edge. Okay, is that clear to all of you? Let's try to see which are simple graphs and which are not. And you have to give me, like I'll just make some graphs here. You'll have to tell me which are simple, which are not. Okay, let's number these graphs 1, 2, 3, 4, 5. Tell me which of these graphs are simple graphs. Write in the chat. Which of these graphs are simple graphs? Okay, is 1 a simple graph? No, because it has a multi-edge, so not. Is 3 a simple graph? No, because it has a multi-edge. Is 5 a simple graph? No, because it has a self loop. So 4 is a simple graph and 2 is a simple graph. Now you've all understood, you all studied trees. Can you tell me, is a tree a simple graph or not? You all studied trees, right? Cool. Right. So you all understand what's a simple graph now, right? Okay. So we're done with this concept of simple graph. Now let's talk about this, concept of bridges plus articulation points. Okay, and then we'll start with this types of graphs. I think the slide should have been the other way around, like the common terms should have been first and then we should have had that. Okay, so let's talk about bridges plus articulation points. And again, see, here in this class, I'm not trying to give you a formal definition of everything. That's not the goal. The goal of this class is to give you enough information about common terminologies so that when you look at a code forces problem, you don't feel lost. You have enough knowledge so that you can tackle a problem. Only the thinking part is required then. Okay. So I'll not be giving you formal definitions here. In case you want formal definitions, you can Google all of these terms up. But here it's more of the understanding part. All right. So let's try to understand what's a bridge. let's try to understand what's a bridge. Okay, so if you look at this, and I think I should be covering bridges and articulation points after I cover connected components. Yeah, let's not cover bridges and articulation points right now. Let's cover this in a while. Okay, because then you'll be able to understand it better. Fine. So now, before we move ahead, let's talk about these common types of graphs. Okay, this. So first of all, let's talk about undirected versus directed. Versus directed. When you look at an undirected graph, whenever you look at an edge, the edge doesn't have a direction. So basically, if you have an edge from 1 to 2, you can go from 1 to 2, you can also come from 2 to 1. Basically, this is an undirected graph wherein every edge doesn't have any directions. 1, 2, 3, 4. But this is not an undirected graph. If you do something like this edge going from here to here, this edge going from here to here, and this edge going from here to here. Now every edge has a direction. So basically, if you look at 1, 2, 3, and 4, you cannot go from 2 to 3 in this graph. This going from 2 to 3 is not allowed. Whereas here from 2 to 3 or from 3 to 2, both of these are allowed. Okay, do you all understand what are directed and undirected now? Right, very simple concept. Next is weighted plus unweighted. Weighted and unweighted. So if I draw a graph like this, and I say that every edge now has a weight as well. For example, the weight here could be 2, the weight here could be 3, it could be 5 here, it could be 4 here. Similarly, if I draw a graph like this, which doesn't have a weight, then this is like, this is a normal graph, right? Now, if you look at it, you can, imagine a weighted graph as a country. For example, if you look at India, and then if you look at, the distance from, let's say, New Delhi to Gurgaon. For example, if let's say the distance is 30 kilometers, then this is a weight. This is a weight from the, weight of the edge from Gurgaon to Delhi. Right? A weight is usually denoted by some cost. Like if these are the nodes, 1, 2, 3, 4, 5. And if I ask you what is the cost to go from 2 to 3, you will tell me 5. So that is a weighted edge. Right? So these are the two types of graphs, a weighted graph and an unweighted graph. Weighted graph has a weight assigned to every edge. So basically, whenever you traverse through an edge, you have to pay some cost. That is how you can understand it. Right? Now let's talk about cyclic and acyclic graph. So I think we've already looked at a cycle. What's a cycle? But let's try to see what's a cyclic and an acyclic graph. A cyclic graph is basically a graph in which you can go from one node and come back to the same node by following unique edges. Okay, this is again very, very important, unique edges. If I tell you this, is this a cyclic graph? Yes or no? Is this a cyclic graph? 1 and 2 and just one edge between 1 and 2? No, this is not a cyclic graph, but somebody might say that, okay, I can go from 1 to 2, I can come from 2 to 1 back. Is this a cycle? The answer is no. Because I've clearly told you that a cycle is basically a construction where you only follow unique edges, unique nodes, except for the last node and the first node. The last and the first node are the same, right? So this is not a cyclic graph. So I think somebody was asking here in the chat as well, right? Can we go from 1 to 2 and come to 1 back? Is that a cycle? The answer is no. So this is not a cyclic graph. A cyclic graph is basically a graph in which you can go from one node and come back to the same node again, right? Let's say this. Sorry, this is a. This is also a cyclic graph only because you're not following the same edge again. But let's try to look at this. This is a cyclic graph. Somebody saying, but when we have self loop, see, a self loop is like a unique type of cyclic graph. Self loop graphs are usually not considered when you look at CP or DSA in general. Like this concept of self loop is really like not really useful. Nobody's going to give you a graph which is going to contain self loops. Because what's a self loop? There is no meaning of a self loop, right? This is like just adding many edges on the same node. It doesn't make any sense. So a cyclic graph, when we say cyclic, just assume it's a simple graph, not a graph which contains self loops. And an acyclic graph is very simple. Like there is no cycle. You cannot revisit a node again by following unique edges and nodes. Okay, I hope this is clear. Now let's talk about this concept of connected and disconnected graph. So connected is very simple. Let's say this is a graph and this disconnected. Tell me one thing. In this first type of graph, if you start from a node, can you go to any other node? Like if you start from this node 1, can you go to any other nodes following some edges? 5, 6. Yes or no? If you want to go from 1 to 5, can you go following some edges? If you want to go from 3 to 6, can you do that? Yes. But tell me one thing, if you have 1, 2, 3, 4, 5, 6, in the second graph, can you go from 1 to 6? The answer is no. So connected, disconnected is very simple. In connected, if you start from a node, you can go to any other node following some edges. But in disconnected graph, there is a disconnect. Basically, you cannot, if you start from a node, it is not guaranteed that can you visit some other node or not. Okay. So yeah, this is connected, disconnected, and let's now talk about a complete graph. A complete graph is again very simple concept. Yeah, so a complete graph is like this. Basically, if you look at any node, the neighbor of any node is equal to the entire graph minus x. Are you able to understand what I'm saying? Now I'm talking in terms of symbols. I've told you what is a neighbor. I've told you what is, like what is a graph. So what I'm saying is that neighbors of node x are basically all the nodes in the graph except x. Right? So when I say this is node 1, 2, 3, 4, the neighbor of 1 should be 2, 3, 4. Basically, there should be an edge from 1 to, all the other nodes. Neighbor of 2 should be, 1, 3, 4. Neighbor of 3 should be equal to 1, 2, and 4. And neighbor of 4 should be equal to 1, 2, and 3. Right? So this is like neighbor of x is equal to g minus x. G is the entire graph, and you remove x from it. That's what you get, neighbors of x. Okay, is that all clear to all of you? Undirected versus directed, right? This is clear. Unweighted plus weighted, cyclic plus acyclic, connected plus disconnected, complete graph. Now tell me one thing, if you get a code forces problem, if you look at a graph problem on code forces, will you be able to identify terms? That's the idea. Like, if I tell you that, if I give you a code forces problem, will you be able to understand what these terms mean? Like if somebody tells you that let's say there is an undirected, undirected weighted graph. What do you mean by an undirected weighted graph? Very simple. This would be an undirected weighted graph. This is undirected, but there would be weights to some edges, 1, 2, 3, something like this. Okay. If somebody tells you, let's say, there is a undirected acyclic graph. So is this an undirected acyclic graph? Yes or no? Undirected plus acyclic graph. Is this an undirected plus acyclic graph? No. This contains a cycle. Okay. So this is the main aim of this, very short things. Some things that I've told you. Undirected, weighted, directed, all of these terms. Whenever code forces gives you a problem, they're going to, give you a story, and then they're going to give you hints for you to understand whether the graph is connected, whether the graph is, disconnected, all of these things. So tell me one thing, is a tree, okay, what would you say? Is a tree, let's try to, identify here. Like, let's suppose, let's see what is a tree, okay? If I say tree, so can you tell me whether a tree is directed or undirected? A tree is undirected, first of all. Because, okay, you might have, you can say that if you root a tree and if you assign this direction, let's say you root a tree and you assign the directions as going down, then this is a directed tree, okay? But in general, it is an undirected graph, okay? A tree is an undirected graph. Is it a weighted or an unweighted graph? Depends on the problem. Somebody might give you a weighted tree, somebody might give you an unweighted tree. So weighted plus unweighted, you cannot really identify. So this is not any thing that you can do about it. Is it cyclic or acyclic? It is cyclic. Sorry, it is acyclic. Okay. Is it connected or disconnected? It is connected. Is it a complete graph? No. Okay. So now do you all understand what do I mean by all of these terms? You just have to basically, whenever you're given a code forces problem, you just have to understand what is the problem trying to say. If it gives you a tree, all of these terms should click in your mind that a tree is some sort of this type of graph. All of these terms should click in your mind very, very instantly. And obviously we have 3 weeks for graph, so this class might seem very basic, but these terms are very important. Okay, I'll come to this point again, bridges plus articulation point, once I cover connected components. Okay, now I have some results for you. And I want you to understand whether these results are true or not. So an undirected graph, again, these results are not something that anybody will tell you. These are results that you will identify with experience. Okay, when you Google something like results for graphs, you will not find all of these terms. Okay, you will have to experience it, and you will have to solve a lot of problems, and you will have to then analyze which are some common results. So I'm giving you 3 common results already. Okay, so the first common result is that an undirected graph where each node has at least degree 2 will contain a cycle. How many people are able to visualize this on their own? That an undirected graph with every node having degree at least 2. Basically, every node has at least 2 neighbors. This is going to contain a cycle. Okay. Anybody who disagrees with this or is not able to visualize it, write a -1 in the chat if you are not able to visualize this. That any undirected graph which has degree at least 2 is going to contain a cycle. Do you want me to prove this? Or is it making sense already? Because if it does make sense, then there's no need to prove it. Okay. Let's try to prove it, because I don't see a very positive result here. So what I mean to say is that consider any graph where every node has degree at least 2. Every node has degree at least 2. It is going to contain a cycle. Okay, how do I prove it? Consider any graph. Okay, consider any graph that comes to your mind and consider the longest path in it. Okay, so let's say this is a graph. Again, like every node has to have a degree of 2. So if I draw a graph, then it is obviously going to contain a cycle. So that wouldn't really serve the purpose. But let's try to consider an how do I put it, an argument here. So consider any graph G with every node having degree greater than or equal to 2. Okay, consider any such graph and do one thing. Start from any node X and find the longest path in the graph. Okay, do one thing. Start from node X, keep going forward, find out the longest path in the graph, keep going forward, like as long as you can. Now tell me one thing, when you have found out your longest path, okay, when you have found out your longest path, this is node 1, and let's say this is node X at which you reach at the end. I mean, let's call this node X and let's call this node Y. So you want to construct the longest path starting from node X. All right, you start from node X, you keep going forward, keep going forward, keep going forward, keep taking unique edges and unique nodes, and you end up at Y. Now tell me one thing, if I tell you that every node has a degree greater than or equal to 2, every node has a degree greater than or equal to 2, so can I say Y is going to have an edge to any one of these nodes here? Like this combined thing. Y has to have a degree of 2, right? At least 2. So I have just used one of its degree. I started from X, I ended at Y. Now, if you are saying that this is the longest path, you have to consider the argument here. If you say this is the longest path, then it clearly means that if you visit any more nodes after Y, there's going to be a repetition. Right? If there was a possibility of going to node Z, then X to Y wouldn't have been the longest path. X to Z would have been the longest path. Right? Now, if you're saying X to Y is the longest path, then it means that you cannot extend this path further without revisiting some node. But you initially said that every node has a degree greater than or equal to 2. So that clearly means Y has to have an edge with any of the already visited nodes. If Y has an edge with any of the already visited nodes, can I say it is going to have a cycle? Yes or no? I am saying consider any graph, consider the longest path starting from X ending at Y. If it is the longest path, then it cannot be extended further, because extending it further would revisit some of the node, right? But we have also saying that if it is ending at Y, it has to have, Y has to have another edge, right? This Y node, this has to have another edge. So it is only going to have an edge to some already visited node. So that's why it has to have a cycle. So does this argument make sense to all of you? Write a +1 for people who are able to understand this. That any undirected graph with degree at least 2 is going to contain a cycle. Okay, what about others? Like, I see very few +1s, only 2 +1s. Are others able to follow this or not? Okay. Now, similar argument you can, give here that a directed graph. Just a second. Yeah. A directed graph where each node has at least one in degree and at least one out degree. What do you mean by in degree? In degree basically means that, if you are saying 1 and 2, then in degree of 1 here is 0 and in degree of 2 is 1. Basically, there is an edge coming into 2, right? Similarly, an out degree of node 1 is 1, but out degree of node, for example, if you consider another edge here, let's look at it like this. 1, 2, and 3, then I can say that in degree of 2 is equal to 2, in degree of 3 is equal to 0, in degree of 1 is equal to 0. Similarly, out degree of 1 is equal to 1, out degree of 3 is equal to 1, there is an edge going outside 3, and out degree of node 2 is equal to 0. Okay, so similar is the argument here. A directed graph where each node has at least one in degree and at least one out degree will contain a cycle. Okay, so for this, this is something that you can analyze for homework. This is very similar to the argument that I've given you, the longest path argument. Okay, if you have to prove a lot of graph problems, some ideas that you have about graphs, there is this concept of longest path trick. This is a longest path trick. Longest path trick. So basically, what the longest path trick is that you consider the longest path starting from X ending at Y, and then the argument here is that the path cannot be extended beyond Y because it is going to revisit some node. And also another argument here is that X to Y is the longest path in the graph, right? So then you can form certain arguments about it. Okay, this is something that you'll learn with experience. I wanted to just share some cool results, because when I got to know this and I could see that this result was being applied in a problem, then I felt kind of really happy about it, that I felt really excited about this result. Okay. Another result is this, that the sum of all degrees is even. Basically, if you look at any graph, then the sum of all degrees, basically if you do something like degree of X, summation of degree of X, X being like X is an element of G, then this comes out to be even number. Any argument on why this is true? Why this is true? Because every edge that is there in the graph, every edge corresponds to an addition of 2 in the entire degree, right? Exactly. One edge increases degree by 2. So since a degree only increases by 2 every time you add an edge, so the overall number would be even, right? And obviously we'll have more results for, as we move ahead. Cool. Any doubts so far? Write a +1 in the chat if everything so far is clear to all of you. Okay. So now let's try to understand the representation. How can you represent a graph? Okay. Like how do you take an input from a problem? How do you represent it? All of these things. Okay. I think there's a lot to be discussed, but yeah. So first is the adjacency matrix. So let's consider a graph. Let's say this is the graph. Or let's consider, a smaller graph. This is 1. Five. Okay. So what you do in an adjacency matrix is that you make a 5 cross n matrix. Okay. Now, whenever there is an edge between two nodes, like, this is 1, 2, 3, 4, 5. And this is 1, 2, 3, 4, 5. Whenever there is an edge between two nodes, you add 0. You add 1 there, otherwise you add a 0. So basically, if you look at the adjacency matrix for this graph, it would come out to be 1 to 2, there is an edge. So, I mean, this is 0. Let's put these as zeros. This is the diagonal. So we say there are no self loops. Okay. Then we say from 1 to 2, there is an edge. So we write 1 here and 1 here. We say there is an edge from 2 to 3. So we write, 2 to 3, 1 here and 1 here. Then we say there is an edge from 2 to 4. So we write, 2 to 4, 1 here and 2 to 4, 1 here. Then we say there is an edge from 1 to 5. So we write 1 to 5 here, 1 to 5 here. Rest, I don't think there are any more edges. 1, 2, 3, 4, 1, 2, 3, 4. Yeah. So this is an adjacency matrix. Are you able to understand what's an adjacency matrix? You write a 1 where there is an edge. You write a 0 where there is no edge. Okay. Similarly, let's say I tell you there is a weighted graph. Okay. Instead of saying that there is an unweighted graph, if I tell you there is a weighted graph, let's suppose I assign the weights as something like, let's suppose the weights are 2, 7, 8, and 9. Let's say these are the weights. So instead of writing 1 and 0, you can write the weight and 0. Fine. So if you were to change this entire, adjacency matrix, you would write something like 1, 2 is how much? 7. Yeah. 1, 2 is 7. So then we say 2, 4 is 8. 2, 4 is 8. Yeah. And then we say 1 to 5 is 2. And then 2 to 3 is 9. Okay. So this is how you represent this entire thing in an adjacency matrix. You consider a 2D array and you say that between any two nodes, if there is an edge which is unweighted, this matrix is going to be symmetric. Like if you consider this thing here, this is symmetric along this diagonal. So yeah, this adjacency matrix is a symmetric matrix. I think this is very obvious that this is a symmetric matrix. Like if you take a mirror reflection, that's what you get from the left diagonal to the right diagonal. So yeah, that's a good point. Let me write it here. Symmetric. Okay. So this is very clear, right? This adjacency matrix is a symmetric matrix. Tell me if you were to, if you have to add a fresh edge to the graph. Let's suppose there is a fresh edge in the graph from 2 to 5. Okay. How much time would that take to update the entire matrix? If there is a fresh edge in the graph now, just order of 1, you will just, let's say this comes out to be 10. So you will just, go to 2, 5. 2, 5 is here and you'll make this as 10. And 2, 5 is where this 10, right? This is the only change that you'll make. So adding an edge is how much? Order of 1. Correct. But, tell me one thing, if you were to check, or if you were to basically, how do I put it? If you were to list all the edges in the graph now, let's suppose the edges are there. Now, if you were to list all the edges, how much time would that take? The edges are already added into the adjacency matrix. How much time would you take to list all the edges now? The answer is n into n. Because for every row, you will have to go and check whether there exists an edge or not, right? So that is going to take n into n time in order to list all the edges. Fine. So, I mean, you all understand what's the time complexity of all of these things, right? Adding an edge into the graph is just order of 1. And checking whether there exists an edge. Okay. Checking whether there exists an edge is how much time? If there is an edge from 2 to 3, how much time would that take? Order of 1. Okay. So let me write these things here. Adding an edge E is order of 1. Checking whether there exists an edge between two nodes is order of 1. Listing all edges is order of n into n. Okay. Does that make sense to all of you? This is very simple now. Okay. Let's consider another example, and which is that of an adjacency list. Okay. Adjacency matrix we've covered. Again, see, I can tell you how to code all of these things, but it doesn't really make sense if I start coding an adjacency matrix right now. What we can do is when we discuss, let's say DFS or BFS, like when we discuss traversals, that is the time when I can show you how to take in the input of a graph and all of these things. So I'm not going to code all of these things. Okay. I mean, this should be very obvious that how this 2D matrix is constructed. You just have to make use of a vector or something like that. Okay. Let's consider an adjacency list with vector. So in the same graph, what do you do? Let me put it here. Okay, let's talk about it. Let's make an adjacency list now. Okay, so instead of writing, all of these things like this, do something like this. That let's first of all consider the unweighted thing, and then let's consider the weighted. So instead of having a 2D, matrix, just do something like this. That one has an edge, that let's say 1, 2, yeah, 1, 2, 3, 4, 5, and just write whatever edges exist. So for example, for 1, the edges are, the edges are 2 and 5. For 2, the edges are 1, 4, and 3. For 3, the edges are 2. For 4, the edges are 2. And for 5, the edges are 1. Okay. Are you able to understand what I'm saying? You basically make a vector of vector or an array of vector. Basically something like this. Vector of vector. Let's say int edges. And this has a size of n. So basically for every, every node X, you have a vector. You have, a non-static list of nodes that it has an edge to. Are you able to understand what do you mean by an adjacency list? Okay. Yeah, you can also do something like this. Vector of int adjacency n plus 1. Yeah, this will also work. A vector of arrays. Sorry, an array of vectors. This is what you're writing, Ritesh. You can make a vector of vector or an array of vectors. And for Java people, this is like an array list. A vector is an array list. And for Python, this is a normal list. Okay, now let's try to understand the same things. Adding an edge. How much time does adding an edge take? Like if I were to tell you that add an edge from 1 to 2, right? And how much time will that take? Adding an edge from 1 to 2. Again, this is just order of 1. Okay, if I were to say add an edge from 2 to 5, for example. So what you will do is just you will go to 2, you'll add a 5 here, and you will go to 5 and you'll add a 2 here. As simple as that. And what are you doing? You're doing a pushback in the vector. This is a non-static list, so you're just doing a pushback in the vector. Right? So adding an edge again is order of 1. Tell me one thing, in order to check whether there exists an edge, how much time will that take? Does there exist an edge from 2 to 4? The answer is order of n, because you'll have to go to the adjacency list and you'll have to search in it whether this exists or not. Right? Okay. So, and in order to list all the edges, how much time will that take? In order to list all the edges. So adding, adding E takes order of 1. Checking E, whether there exists an E, takes order of n. But listing all the edges takes order of m. If I were to say that m is the number of edges in the graph, okay? N is the number of nodes in the graph, m is the number of edges. So let's write it here. Sorry. And m is equal to number of edges, okay? So in order to list all the edges, this is going to take just order of E. Why? Because you're going to go to 1, you're going to list all the edges. You're going to go to 2, you're going to list all the edges. 3, 4, 5, so on. Okay, does that make sense to all of you? These two types of representations? Yes, write a +1 in the chat if this is clear so far. Okay, now I'm going to give you a unique way of representation, which is going to tackle everything. I mean, all of these three things. Okay, I'm going to give you a unique way of representation. So we looked at adjacency list, adjacency matrix. We looked at adjacency list with set, vector. Let's consider an adjacency list with sets. So you all understand what's a set, right? A set is an ordered list, basically. Okay, so now let's consider a an adjacency list with a set. This is the most interesting part, actually. I think. Okay, I think I removed the wrong page. Why is this so bad? Okay, so for this case, adding an edge takes order of 1, checking an edge takes order of n, and listing all the edges takes order of n. Okay. So now let's consider this case of adjacency list with set. This was with vector actually. Now let's consider adjacency list with set. So let's copy this again. Yeah. Now, for doing an adjacency list with sets, what you do is you make something like, a vector of sets or an array of sets, something like this, set int adjacency, let's say something like n. You can make something like this, or you can make, let's say, a vector of set of n. Okay, something like this. Now do one thing. For one, what you do is you keep all the things in a sorted order. You say I have edges to 2 and 5. For 2, you say I have edges from 1 to 4, comma 3, sorry, 1, 3, 4. For 3, you say 2. For 4, you say 2. For 5, you say 1. Okay. Now tell me one thing. If you have to add an edge in the graph from 2 to 4, how much time will that take? From 2 to 5? Log n, correct. How much time would that take to check whether there exists an edge or not? Again, log n. And how much time would it take to list all the edges? Order of m. Right. Okay. So are you able to understand what I'm saying? Like, just by changing a vector to a set, you are basically, changing these things. You're going from adding an edge to log n instead of order of 1, you're going log n. But then checking an edge becomes log n as well. And listing all the edges remains the same. So are you able to see like how we're making a trade-off here? Okay. Is there anybody who could not understand this part? Adding e would take order of log n. Checking e would take order of log n. And listing would take order of n. Okay. For how many people this was new, that this is something that you can do? For example, I know some people would already know how to represent the graph. So for those people, was this new, that you can do the same thing with a set? Okay, cool. So we've looked at this thing, and we've looked at the pros and cons. Basically, I think this is already clear, like using time and space complexity, like time complexity, all of these things should be clear. So basically with set is going to be beneficial mostly. No. See, Ritesh, in a lot of problems, this is not the requirement. This thing, checking E, this is not the requirement in most of the problems. So if this is not a requirement, then why not just have a normal, adjacency list with a vector? This. In case this is a requirement, checking whether there exists an edge. So I think Aman said that he used this in AdCoder. So Aman, was this the requirement there? Checking whether there exists an edge A to B or not? Was this a requirement in your problem? Yes. So if there is a requirement, then making use of adjacency list with a set is a preferred thing. But most people, I think 99% problems you will solve using this, or 90%, let's say, you'll solve using this thing, adjacency list with a vector, not a set. Okay. I hope this is clear to all of you now. So far, everything. In the tree, we had normal vector. Yeah, exactly. In the tree, you had a normal vector of int, right? Adjacency n plus 1. That's how you store a graph as well. Nothing different, but this is just a new representation. Again, see, when you look at a tree, now again, that, if you were to have a problem with checking whether there exists an edge or not is required, then you can again use a set, right? So there is no convention that a set is only used in a graph. It can also be used in a tree. Okay, so now let's talk about, these traversal techniques. Also, before we move ahead, do you have any doubts so far? Because if yes, then I can address that first and then I can move ahead. So I'll give you a 2-minute or a 1-minute breather now, and you can list all your doubts in the chat. Okay, so somebody's saying, what if you use adjacency matrix along with the adjacency list? Okay, so you're saying you store the graph in two places. First as an adjacency matrix and second as an adjacency list. So then checking an edge becomes order of one, right? The problem here is that if you look at an adjacency matrix, listing all the edges becomes order of n square. And similarly, when we look at something like a DFS or a BFS, you will see that both of these algorithms become order of n square with an adjacency matrix. So I'll come to that part. And again, like Aman is saying, that also will give you a memory limit exceeded. Because how much memory are you using? With an adjacency matrix, how much memory are you using? You're using order of n square memory. Whereas with an adjacency list or an adjacency list with a set, you're using only order of m, which is the number of edges, right? So with an adjacency matrix, you also get a memory limit exceeded if n is exceeding, let's say 10 to the power 4. All right. Cool. So now let's talk about DFS, BFS, and application of these traversals. So first of all, let's look at a DFS. Okay. So what happens in a DFS is that you basically, if you look at a node, like if you look at this graph, just give me a second. I'll just. Yeah. So if you look at DFS, there are two types of traversals in a graph, a DFS and a BFS. Let's consider a graph first. Okay, this is node 1, 2, 3, 4, 5, 6, 7, and 8. So what you do is you start from, let's say, node 1. Okay, you start from node 1. Then you choose any of these directions, okay, let's do it like this. Let's make it interactive. Which direction do you want to go to? Do you want to go to 2, 3, or 8? This is a traversal that we're doing in a graph. We want to go to other nodes. So which node do you want to go to? Let's suppose we go to 3, okay? Now, starting from 3, which node do you want to go to? You have an option of 4 and 5. 1 is already visited. Okay, you come here. You go from 1 to 3. Now let's say you go to 4. Okay. Yeah. Now tell me one thing, can you visit any more nodes after 4? If you've reached 4, can you visit any more nodes after 4? Without revisiting any node. So basically you start from here, you go to 3, then from 3 you choose this direction. So basically you're going in the depth, okay? If you look at it, you're going in the depth. This is known as a DFS, depth first search. So if let's say you had to check, okay, let's suppose this is the problem. Check whether there exists a path from 1 to, let's say, 7. Let's suppose this is the problem. Okay, you want to check whether there exists a path from 1 to 7. So what you do is you do a depth first search. So let's say you start from 1, you go to 3, and then you say from 3 I will go to some depth. Let's say you go to 4, and you realize that after 4 there is no node that you can visit. So what you do is you revert back to 3. You say now you start searching in some other direction. So from 3, let's say you go to 5, then from 5, let's say you go to 6, right? And then from 6 you go to 7, and then you see that okay, I've reached 7. So yes, there exists a path from 1 to 7. Right. Similarly, if you had to check whether there exists a path from 1 to 8 or not, you could have done something like this, that you went from 1 to 3, then from 3 to you went to 5, then you went to 6, then you went to 7, and you realize, okay, there is nothing beyond 7. So you come back to 6. You realize there is nothing beyond 6 that can be visited, you come back to 5. Then you realize that nothing can be visited again, you come back to 3. Okay. Then from 3, you realize, okay, you can go to 4. So you come here. But then from 4, you realize that there is no node that you can go. So you come back to 3. Right. Then from 3, let's say you come back to 1. Then from 1, you have a choice again. You can either go to 2 or you can go to 8. Let's suppose you go to 2 and you realize there is nothing. Okay. So you come back to 1. Then you go to 8 and then you realize, okay, I've reached 8. So yes, there does exist a path from 1 to 8. So are you able to understand what is happening in depth first search? You're starting from a node and you keep going inside. Okay. Until you hit a point wherein you cannot explore any more nodes. When you hit that point, you revert back. you go back to the previous parent that you have come from. And similarly, by doing like this, you can search whether there exists a path from any node to another node or not. Fine. Is it clear? Okay. So if you were to if you were to consider this thing, let's make another graph. Let me make a graph and let me ask you if this is a valid DFS traversal of this graph or not. One, two, three, 4, 6, 7, and 8. Okay. Let's suppose these are the nodes. Tell me if this is a normal, if this is a correct DFS traversal or not. You go to node 1, then you go to node 4, then you go to node 5, then you go to node 6, then you go to node 2, then you go to node 7, then you go to node. Let's suppose this is the traversal that I'm saying. Is this a valid DFS traversal? No. Why? Because you start from 1. Okay, this 1 is correct. You go to 4. Okay, this 4 is correct. You go to 5. Okay, this 5 is correct. But now, since there are no more nodes that you can visit after 5, so you revert back to 4. We will not call this a visiting exactly. But then you come to 6. So this is correct. Then they're saying, okay, you go to 2. But no, we have some more nodes which need to be visited below 2, right? Below 6. So this is not a correct DFS traversal. Okay, so this is not. What about this traversal? 1, 4, 6, 7, and 5. Is this a valid DFS traversal? No, this is again not. Why? Because you're coming from here, then you're going from 1 to 6, then from 6 you're going to 7, but then you're going to 5. No, this is not allowed. Okay, so this is again wrong. Is this a valid DFS traversal? 1, 2, 4, 5, 6, 7, 8, and 3. Yes. Why? Because you start from 1, you go to 2, you come back to 1, but this you won't count as visiting again. So you go to 4, you go to 5, you come back to 4, you go to 6, you go to 7, you go to 8, you go from, okay. From 8, now you might say that, there is an edge from 8 to 6. So can I explore that? The answer is no. When you're doing a DFS traversal, you basically try to encounter unique nodes. So you only visit a node when it hasn't been visited before. Okay, why? Because see, you want to find whether there exists a path from 1 to 8 or not. If you've already visited 6, would you want to visit it again? The answer is no, right? So you come to 7 again, you come to 6 again, you come to 4 again, and then you come to 1 again, and then you go. So this is a valid DFS traversal. Okay, clear to all of you? Okay, let's try to look at the code for DFS. And again, see, this is going to be very, very similar to. So here we need this visited array. Yeah, I'll come to this. So let me first of all share a different screen. Just a second. So can you let me know if my screen is visible? Okay. So what we'll do is we'll take in the input of a graph, and I will also show you how the visiting, or I mean basically how an input of a graph is given. So first of all, you give the input of the number of edges. Number of nodes in the graph. Let's say there are 5 nodes in the graph, and there are 6 edges in the graph. The edges are, let's say the edges are 1 to 2. There is an edge from 2 to 3. There is an edge from 3 to 4. There is an edge from, let's say, 1 to 5. And then let's say there is an edge from 1 to 6. And then let's say there is an edge from 5 to 6. Okay. So this is the graph. Now what you do is you take in, and now we are going to construct, adjacency list here. Fine. So we're going to take in a vector of vector. Let's first of all take in the input in nodes, edges. And let's put it like this, n comma m. So this is the number of nodes and number of edges. Now you make an adjacency list. Okay. Okay, this is an adjacency list now we're making. What you do is you go for number of edges and you take in the input of edges. So you say there is an edge from U to V. What this means is that there is an edge from U to V, but we are looking at an undirected graph. We are not looking at a directed graph where there is an edge from U to V only. When we say there is an edge between U and V, it means that there is an edge from U to V and also from V to U. So what we'll do is we'll say edges of U dot pushback V, and we'll say edges of v dot pushback. Okay, this is how an adjacency list really works. And another thing here is that we've taken one based indexing, so it should be like you have to make it based, right? So what we'll do is we'll do u minus minus and v minus minus. So we'll be looking at zero based indexing in the entire problem, right? Now, if you want to, let's say, do a DFS traversal from node, something like 0, basically node 1. Okay, if you look at this is node 1, or in fact, let's not do it like this. Let's just 0 to 1, 1 to 2, 2 to 3, 0 to 4, 0 to 5, and 5, 4 to 5. Let's suppose these are the edges. Let's not do this u minus minus v minus minus. These are the nodes. Okay. Now what you do is you do a DFS traversal from node 0, and you pass in the edges, and you pass in, another thing here is that you already studied trees, right? You all have studied trees. So how you do a DFS traversal is that you pass in the parent here. You say that I'm going to pass, let's say, -1, and then I'm not going to, basically in order to avoid revisiting the parent. But here you must understand that the graph can contain a cycle as well, right? This is not as simple as a tree. So the graph can contain a cycle as well. So you need to keep track of the nodes which have already been visited, right? So what you'll do is you'll make another, let's say an array of Boolean array. Let's call it visited. So all of these are filled with false. That means that none of the nodes have been visited right now. So what you do is this, and let's suppose, you can basically print whenever you visit a node. So what we do is void DFS int current node. Okay. The first thing that you do whenever you visit a node is that you mark it visited. Now all you have to do is this: you have to iterate over the edges. And the first thing that you do is you first of all check if not visited of E. Basically, if you're going to E, then E should not be visited. So what you do is you do a DFS from E edges, and similarly you can maybe print whatever node you're visiting. Okay, so this way you can identify the DFS traversal. So let's try to see what are we getting as output for this. So it says you visit node 0 first. Okay, do I have to really draw it on the iPad, or can you visualize it on your own? Basically, it's like saying you have an edge from 0 to 1, then from 1 to 2, and from 2 to 3. Then you're saying you have an edge from, to, what is this, 0 to 4. And you also have an edge from 0 to 5. And there is also an edge from basically 4 to 5. Okay. Then this was. This is how the edges are working. I mean, this is an entire edge, okay, from 4 to 5. So what you do is you start from 0, you visit 1, you visit 2, you visit 3, and then you visit 4 here. You visit this 4, and then you visit this 5. This is how the DFS traversal looks like for this graph. Okay, clear? Is the code clear to all of you how a DFS works? Basically, I think you have already studied trees, so this might seem more, like, how do I put it? Understandable, right? So this is a DFS. Okay. Now let's come to something known as a BFS. So let's stop sharing this and let me share this one. What happens in a BFS is that if this is the graph, you basically, let's say, start from this node. Then you visit all the neighbors that are away from you by just one edge. So basically you visit this node and then you visit this node. Okay. So if the nodes are numbered 1, 2, 3, 4, 5, 6, and 7, you basically visit the nodes in this order. First of all, let's say you visit 1, then you visit 2, 3, and then from 2, 3, whichever nodes you can visit by just following one edge, you visit them. So basically in this case, you will visit 4, you will visit 5, and you'll visit 7. Okay, so then you say you visited 4 comma 5 comma 7. Now with the new edges, with the new nodes that you've encountered, 4, 5, and 7, you try to see which are the other nodes that you can visit by just one edge. So which it comes out to be 6. Okay, so this is how it works. Okay, so for DFS, it is like, you keep going into the depth, whereas for BFS, you do the breadth first search. So if you were to consider demarcation, then let's make a tree only for now. This is 1, 2, 3, 4, 5, 6. So a BFS could look something like, 1 comma, let's say 3 comma 2 comma 4 comma 5 comma 6. Whereas a DFS would look something like, 1 comma 3 comma 5 comma 6 comma 2 comma 2 comma 4. Okay, does that make sense? See here, this order doesn't matter. 2 comma 3 comma 4 can be visited in any of the orders. It could be 2 3 4, 3 2 4, or 4 2 3, anything, doesn't matter. And if you look at DFS, you first of all have to visit the entire depth, and only then can you revert back. Any doubts on DFS versus BFS? Any doubts on this? Okay, no. Cool. Now let's talk about this concept of application of traversals. So you've looked at DFS, you've looked at BFS. Let's try to also look at the code for BFS. Okay. So you also need to ensure that there is, like, if you look at a BFS, there is this concept of levels. Let's suppose this is level 1, then this is level 2, then this is level 3, then this is level 4. Right. So basically, you need to visit nodes in an order. All right. So what you can do is that you can make use of a queue here. Let's suppose this is a queue. So inside this queue, let's suppose you pushed 1 first of all, and you realize that, okay, this is the node 1 that I have to look at. So you pop out this node 1 from it, you put it in the BFS traversal. Then you look at what are the neighbors of 1 which are unvisited, and you see this is 2 and 3. So you put 2 comma 3 in the queue. Now you look at 2 and you see that you pop out 2, you put it here, and then you look at all the neighbors of 2 which have been unvisited. So you look at 4 and 5. So you add them in the queue, 4 comma 5. Then you go for 3 and you say that which are the nodes that are unvisited, and you realize that for 3, like, you pop out 3, put 3 here. You see the only node which is unvisited is 7, so you put 7 here. Similarly, you go for 4, you put it here, no other nodes can be visited. You go to 5, you put it here, and you see that, okay, another node that can be visited is 6. You put 6 in the back of the queue. Then you pop out 7, you put it here, and then you basically pop out 6 at the end. Okay, so let's just quickly code it up. Very simple stuff. So again, the same thing here, but we'll just make use of a queue. Okay, tell me one thing: is the use case of a visited array important here or not? Like, do we really need the visited array or not? We don't want to still visit any node again. So we do need the concept of visited array here. So what you do is, first of all, let's say you insert 0 inside this, and then you start from this queue, and you just say while not queue.empty. You pop out the first node. You print it first of all, and then you say visited at top is equal to true, and then you just iterate over all the edges. And I think this should not be here. Mark it here because it's already visited. And then you say, first of all, you mark it as visited because you already put it in the queue. And then you say queue dot push, and that's it. So let's try to see what are we getting here. I think we also need to pop out from the queue. Visited, yeah, visited, actually. Okay, so here in this case, you're getting 0. See, first of all, you started with 0, you got 1, and then you got 4, and then you got 5. So the level 1 is cleared, and then you go for 2 and then. Okay, any doubts in this BFS stuff? See, all of these things are very simple, and all of these things are going to be foundation of what you're going to do ahead. So this is like DFS, C.CPP is DFS, and D.CPP is BFS. All right. So now let's try to look at the same thing again, and let's try to see the applications. So the first application of traversals is, checking for connected components in the graph. So let's try to see. Connected components. So let's suppose I give you a graph like this. Okay. Let's make it like this. This is the entire graph. Okay, this entirely is a graph. Tell me one thing: is this graph connected or disconnected? This graph is disconnected, right? So now, what you might want to, this might be relevant information for you, which is to check which component node lies in. For example, if I name this component 1, if I name this component 2, and if I name this component 3, it would be useful, like in a lot of problems, to see which component a node lies in. For example, if you mark all of these nodes as node 1, like if you mark this entire component as 1, if you mark this entire component as 2, and if you mark this as 3. Okay, so this is like checking for connected components, like basically distributing the graph into its connected components and having a unique identifier for each of these components. Somebody saying we can make visited array of int type while marking, we mark that. Yeah, you can do that. Exactly. You can do something like this. Yes, Aman. So tell me one thing, can you do this using a DFS? Like basically what you do is that, let's say, first of all, let's number these nodes in the normal sense. Let's suppose the nodes are 1, 2, 3, 4, 5, and 6. So what you do is you start a DFS from node 1 and you basically visit all the nodes that are possible. So basically you start a DFS from node 1, you visit 1, you visit 2, and then you visit 5. Okay. Can you visit any other nodes after visiting node 5 in the DFS which you started from 1? No. So now you go for 3. You say, okay, 3 is unvisited, so you start a DFS from 3 and you go for 4. Similarly, then you go for 6. So this way you will be able to separate out all the nodes into their respective components. Somebody saying DFS in a loop along with count. Yeah, you can do something like that. So let's try to code it up. I'm not going a lot into the depth here because see, now it would be more of coding, less of explanation. So let's try to do one thing. I hope my screen is visible, right? Let me share it again. So now do one thing. Let's just copy this code. Let's do like this. Now, what you can do is that you can maintain, let's say, a count, and let's put it like this: vector int component. Here we'll just store which component a node lies in. So we can say n, and we can maintain a count here. So instead of doing a DFS for just 0, we'll do a DFS of all the nodes now. And we just say if not visited, at I, do a DFS from I, edges, and visited. And also pass this count here. Okay, and then do a count plus. So what this will do is that in all of these components, it is going to basically add which component it lies in. So also pass in components here. Firstly, what we'll do is we'll set visited at parent is equal to true. then we will say component at cur is equal to comp at cur is equal to count, the value that we passed, and then we'll just pass in count. Then at the end, let's just print the components. So right now, this is the graph. And if you look at the components should all be 0. Basically, every node is in the same component. Let's try to, remove some edges and see what happens to the graph. Let's suppose we have only 5 edges, and let's suppose we remove this edge from 2 to 3. So what do you think is going to be the output? 3 is going to just have, a different component. So let's see. Basically, this is the graph. This 3 is separated out. Okay. Now let's try to separate out 4 as well. Let's try to remove, let's say, suppose this edge. This is bad. Let's suppose this is the graph now. Okay, 4 and 5 are also separated, for example. So now you just have 2 edges. Let's see what do we get as now. So 0, 1 and 0, 1, 2 are in just component 0 here. This node 3 is in a different component 1. Sorry, I think we have some problem here. There should be 6 nodes, right? Yeah, the nodes have to be 6, not 5. Right? Yeah, I think we made some problem here. So yeah, this is how it is going to look like. Is this clear? Component stuff, connected components? Right? Okay. Tell me one thing, how do you detect a cycle now? If you were to check whether there exists a cycle in the graph or not, how do you check it? How do you check for a cycle? In a simple graph, obviously, not in a graph which contains self loops or multiple edges. How do you detect a cycle now? We store parent node and check if parent equals to cur, then cycle. No. Like, see, you're adding 2 edges here, okay? You're adding an edge from U to V and also from V to U. So just doing that would not work. If we visit a vertex again, so see, again, this is not really going to work, because if you have a graph like, let's say, let me share my iPad screen and then this will make more sense. Now you're checking for cycle detection, okay? Just checking whether a cycle exists or not. So if this is the graph, you have 1, 2, 3, and 4. Okay. So you start from 1, right? You start from 1, then you go to 2. And then from 2, you basically, you can go to 1 and you can also go to 4. So just checking whether you're visiting an already visited node would not work. Would that work? That just checking whether you're visiting a node again. Because see, if there is an edge from 1 to 2, there is also an edge from 2 to 1. So, even though there doesn't exist a cycle, you would just say that exists a cycle. If you just say whether we are visiting the same node again or not. So do you understand that Yogaraj, that this would not work? Just checking whether we are visiting a node again or not. Because if you go from 1 to 2, then from 2 you have 2 options. You can go to 1, you can go to 4. If you say going to 1 is an edge, is a cycle, then the answer is no, it's not a cycle. So like somebody saying, like Ojas is saying, we can maintain a parent if you want to do it in a DFS. So we can again say that as you do it in the case of like a tree, you check whether if you are visiting the parent or not. If you're not visiting the parent, but you're still visiting an already visited node, then that means it's a cycle, right? Okay, so let's try to code this up. Again, very simple. We are only going to change a few lines of code. That's all. We'll just maintain a parent as well. This would not be required. Okay, another thing here is that if you have to check whether there is a cycle in the graph or not, what do you think? Do we need to do a DFS from all the nodes, or just doing a DFS from one node is fine? Like the graph could be disconnected, right? Whenever a graph is disconnected, if you have to do something related to the entire graph, you will have to do a DFS from every single node, right? So we'll have to do a DFS for all the nodes. So we'll say visit it, and then we'll pass in the parent as well. Let's suppose we pass in the parent as -1. So now all we do is that here we just check. If not visited E and parent is not equal to E, then you do a DFS. Or basically what you can do is something like this. If it is a parent, if E equals to parent, then you continue. You don't do anything about it. Otherwise, if it is not visited, you do a DFS. Else you say there is a cycle. Okay, let's try to do it for this code. Let's see if we are getting a cycle or not. And here the parent would be, the parent node for the new DFS. This is not required. Count plus plus. Errors are in. Okay. Let's see if we are getting a cycle in this graph or not. So the answer is no, we're not getting a cycle. Let's suppose we add 2 more edges. Let's suppose we add 3 more edges. We add an edge from 0 to 5. We add an edge from 5 to 4, and then we add an edge from 0 to 4. Would there exist a cycle now? Yes or no? Let's see. So yeah, now there is a cycle. So we're getting a cycle 2 times. Why are we getting a cycle 2 times? Because firstly, we are doing something like we visit. Okay, let's just print what are we visiting. So we visited 0, 1, 2, 5, 4, and then we found a cycle. Okay. Then this 3. How are we getting another cycle? Okay, yeah, because see, when you go from 0, when you go from 4, when you're at 4, you can go to 0, right? So that's a cycle. But then when you come back to 5, you can again go to 4, which is also a cycle, right? So we are going to get cycle 2 times here. Like it doesn't really make a sense, but yeah, the cycle exists. That's what what this means. So this is the case of a cycle, right? So are you able to understand that you can find a cycle using a DFS? Can you do the same thing using a BFS? Not very difficult. Simple stuff again. Like just checking in the same code. I think this d.cpp had this. Here you can just maintain a parents array again. For every node, you can maintain that this is the parent. So like if you were to do this using the same thing, cycles2.cpp, you can just maintain a parents array for every node, and you can just say that I should not visit the same node again. So we'll just say if e equals to parent, then you continue, not really required. But if it is not visited, sorry, if it is visited already, then you say cout cycle found. And also another thing here is that when you're visiting E, you also make that parent of E is equal to top. Now what's the problem? If E equals to parent of top. I think I made some mistake here. Yeah. Okay, is it clear to all of you now how you can do the same thing using a BFS? So you can find videos on YouTube or maybe places wherein people tell you how to do the same thing using DFS, then they tell you how to do it using BFS. It doesn't make sense. Basically, like you can do it you can transition pretty easily once you understand one of them. Okay, any doubts so far, or can we move ahead? I have one question for you. How do you construct a path? Basically, if I tell you that I want a path from 1 to 3, how do you tell me what is the path? Like you can check using DFS, you can check whether there exists a path or not. How do you give me the entire path if I want to go from 0 to 3? Maintaining parent would not work. No, maintaining parent would not work. understand why maintaining parent would not work. Let me show you an example here on iPad. Now we want to do something known as path construction. Okay, we want to construct the path from a given node to some other node. So if you look at it, if like for this might work, but if let's say you had something like this, or for example you had yeah, let's suppose this is the case. I mean, I'm trying to construct a case where we're making just parent would not work. Actually, making parent would also work. Like you can just store that for this particular node, what was the node that I came from, right? So yeah, that would also work. Yes. So like Aman was suggesting, yes, parent array would work. I was just a bit confused in this. So yeah, parent array would work. That for every node, you can, when you visit it, you can make sure that you can say that this is the parent. So from the ending node, then you can backtrack. You can say that okay, this was the parent, and that's how you come back. Okay, so let's try to do it in code. Let's try to do the same thing. DFS stuff, parent wali kahan chali gayi wo cycle thing, and let's just copy it. Path construction. I will tell you one cool way, another cool way on how you can do it. So let's try to put it. This is the parent. So you'll have to maintain an array vector and parent n -1. And then if you have to, let's say, find a path from node, if you have to find a path from node 0 to, let's say, node 3, for example. Let's move this 2 to 3. Let's say we have an edge from 4 to 5. Okay, this is, let's say, the case. So these are the edges. And let's suppose there is an edge from here as well. So this is the graph that I'm talking about. There is an edge from 1 to 4 as well. Fine. You want to find out what is the basically path from 0 to 3. So what you do is you start from 0, you send edges, you send visited, you send parent. Right, and all you do is basically visited at parent equals to true. This is the same. If e equals to parent, not really required. As long as you are visiting a new node, you just say that okay, visited. E is the node that you're visiting new. Edges is what you already passing visited, and this parent. And also what you do is you just say parent of E is equal to curve, which means that you got to this node from this parent. Right? Are you able to understand what I'm saying? This is not required. Now tell me one thing. This can also be checked very easily. If I tell you that the parent of node 3 is -1, what can I infer from that? In this current code, if I tell you the parent of 3 is -1, what would that mean? It would just mean that you never visited node 3, right? Because if parent of node 3 is -1, that means you never visited it, correct? But if you visited it, there would be a parent for it, right? So what you can do is you can first of all say if parent of like we can have an ending. Let's suppose you have end is equal to 3, for example. You can take in the input as well. So if parent of end equals to -1, then you say no path. Or let's take in this end start. We're also providing the start and end. Okay, so let's provide the start and end. The start is 0 and the end is 3. So this is the graph that is saying, and then otherwise we say else while not parent of you start in current equals to end, while parent of current is not equal to -1, you just say print cur, and then you say parent cur is equal to parent of cur. What you're doing is you're basically backtracking from the last node. Okay, let's see. Current is equals to parent of cur, yeah, semicolon. So what are we getting? 3, 2, 1. So basically there was a path from, 3, then it went to 2, then it went to, I think we haven't, just a second, there is some issue here. This has to be first of all start. So current equals to end, you do see out curve. No, while current is not equal to -1, it should be. Right? Is this clear to all of you? Root ka parent. So Ritesh, what do you mean by root ka parent? Like you have a start, you have an end. You basically start DFS from start, and then you basically visit every node and then you mark the parent. Root ka parent -1 hota hai. Haan, you can mark that as -1 because you are starting your DFS from that point, right? So it doesn't really have a parent to start from. जहां से आप स्टार्ट कर रहे हो वहां से उसका तो कोई पेरेंट ही नहीं हुआ ना. Parents here, see the parent here is not defined in terms of routing the tree. The parent here is defined in terms of आप कैसे visit कर रहे हो nodes को. If you start from a node, obviously the parent of that node has to be -1, something not present in the graph. Okay. Similarly, if let's say somebody wanted you to tell what is the path from 0 to 5, right? So the path comes out to be 5, 4, 1, 0. Similarly, if let's say somebody asks you to construct a path from 3 to 4, then it would be 4, 1, 2, 3. Okay, does that make sense to all of you? Path construction. All of these are applications of traversals, and these are very useful. These are very basic, to be honest, for graph theory, but these are all useful. Fine. What is the last thing? Okay, so let me share my iPad screen again, and let me give you a problem. So let's try to look at this problem. So Byteland has n cities and m roads between them. Your goal is to construct new roads so that there is a route between any two cities. Basically, you want to connect the entire graph. Okay. Whenever you see something like this written, where is it? Yeah. Whenever you see something like this written, so that there is a route between any two cities, this just means that you need to connect the graph, or it just means that the graph is already connected. Okay. So what is the question? They're saying that Byteland has n cities and m roads between them. Your goal is to construct new roads so that there is a route between any two cities. Basically, if this was the graph, how many edges do you need to add to connect the entire graph? How many new edges that you need to add to connect the entire graph? The answer is just one, right? So you do something like this. So can you give me a solution for this? Very, very simple, very quick. The answer is just simply number of components, connected components, -1. Very as simple as that of a tree. How many nodes do you need to connect an entire tree? Sorry, how many edges do you need to connect an entire tree of n nodes? N-1. So this is the same thing. Just assume that these connected components, they are already connected. But in order to connect, let's say, x components together into one component, it would require x-1 edges. So is this doable for all of you? Finding the number of connected components, just doing -1, and that would give you the total number of new edges required. Okay, so do we need to code it up, or are you all comfortable in this? Doing on your own, because you've already written the code of connected components very recently. Okay, cool. So let's look at another problem. So you're given a map of a labyrinth and your task is to find a path from start to end. You can walk left, right, up and down. So this is the basically, the labyrinth here. Just a minute. Basically, for example, if they want to go from this A to this B, you want to give a path. So the path here is basically like going L, going down, going right, and up. Okay. How many people can do this on their own? Very simple. Again, same thing. DFS in all valid directions, exactly. How many people can do this? See, this is just a normal grid, and you just have to assume every node as a normal node, right? Like this is a node, this is a node, this is a node. There is an edge between these two nodes, there is an edge between these two nodes, there is an edge between these two nodes, and there is an edge between these two nodes. As simple as that. So finding a path, is that difficult or not? Like write a +1 in the chat for people who can do it on their own, this problem. Is there anybody who cannot do it on their own, or like any doubts in this? Because this is already what we've discussed right now. How to find a path from one node to the other node. This is path construction. But now, I mean, I don't want you to solve this problem. I want you to tell me the shortest path from A to B. I want you to tell me this. So basically, if this was the graph, then, and like, let's suppose this was also this node, this was also this. So basically, there are two paths that you can have. This is blue path or this, black path. Which is the shortest path, blue path or the black path? The black path is smaller, right? So this is something that you can do using a BFS. Like using a DFS, this works for path construction, but it doesn't necessarily give you the shortest path, right? But BFS, when you look at a BFS always gives you the shortest path. Why? Because you're always going to visit nodes in the level form. For example, you're going to visit these two red nodes first. Then you're going to visit these two nodes. Then you're going to visit these two nodes. Then you're going to visit these two nodes, and then you're going to visit this and this B. And that's the time when you realize that, okay, this is the path. So do you want me to do it using BFS, the same thing? Like we will obviously find the path, but we will also find the shortest path. This is this is just a modification that we are doing in this problem. We would do it using a BFS. So now I would like to know how many people can do it on their own. A +1 in the chat. Using this same thing, using a BFS instead of a DFS. Somebody is saying, but we can take a depth variable and update using DFS also. See, Aman, I would recommend you to try this on your own. Finding the shortest path using a DFS is like, is not, how do I put it? A polynomial problem. You cannot solve it using polynomial time. Finding the shortest path in a graph using DFS. Because see, when you look at a DFS, like DFS can, you can go anywhere. Like if this is the graph, let's suppose you are going here, here. I mean, shortest path using DFS is like, I'm not entirely sure, but this is not a really intuitive problem. Because you can go anywhere. For example, if you go from here to here, you visit this node, and let's suppose, or for example, you do something like this. Let's suppose you go here, you go here, you go here, or not this one. You go here, you go here, then you go here, then you go here, then you go here. Now tell me, you've already visited this node. So is it the shortest path to this node? No. The shorter path could have been, like following this red, maybe this red thing. This could have been the shorter path. And another shortest path could be just going from here to here. So this is not really a polynomial time problem using DFS. You cannot do it using, by maintaining a depth variable. I hope that makes sense. Because like you will essentially have to revisit the entire graph every time you encounter the ending node. And this would basically be order of number of paths in the graph, number of paths from start to end. If you do it using DFS, this is how much time complexity it would require. You can do it using recursion, like normal recursive DFS. And but then in that case, you will have to visit all the paths. All the paths you will have to consider one by one. Okay, any doubts in this, or is this clear? Write a +1 in the chat if we can move ahead. Like these two problems, if they both seem doable, the two problems that I've shown you. Okay. And you must also understand that using BFS, like if I were to tell you, there are two things, okay? Find path from U to V, okay? And again, see, we are not talking about a weighted graph here, okay? We are talking about an unweighted graph. Do you all understand what is unweighted, weighted? Weighted graph is the graph in which there will be edge weights, okay? So there is like a BFS would not necessarily give you the shortest path. Like, this, if you look at it, sorry. Yeah, let's suppose this is the graph. Let's suppose this edge is 100, this 1, 1, 1. Then the shortest path from this node to this node is how my solution got accepted on this, on CF using this. Was it based on shortest path using DFS, Aman? Okay, I think I would love to discuss that with you after the class. Maybe I am wrong somewhere, or maybe it was a completely different problem. So I'll have to see. Like, how can you do shortest path in a graph using DFS? I mean, as far as my knowledge is concerned, I don't think that works. That is a not a polynomial problem, polynomial time problem. Okay, but yeah. So I'm talking about okay. If you were to give any path from U to V, you can use a DFS. But if you were to give a shortest path from U to V, then making use of BFS is going to be helpful. Fine. Any doubts so far? Like, these 4 things should be clear. Connected components, path construction, cycle detection, and shortest path in an unweighted graph. So this was the problem. Like, obviously they wanted just a DFS solution, but we also can give them a BFS solution to get the shortest path. All right. Any doubts so far? Just a second. Give me a minute. I'll just give you 1 minute breather, and then we can start with bipartite graphs. Again, this would not take a lot of time. I would just say how much, like 10 more minutes. Okay. So today's class has been a bit longer, but yeah, 10 more minutes, and then we can wrap it up. Okay. So let's discuss bipartite graphs. Right, just a minute. I think there is some problem. Yeah, let's discuss bipartite graphs. So what a bipartite graph is basically very simple. That if you look at a graph, basically you want to separate this graph into 2 sets, set A and set B. Okay, you want to separate this graph into 2 sets such that there is no edge within a set itself. Basically, if let's say this node is in set A, then this node cannot be in set A, this node cannot be in set A. This node has to be in a different set, right? So let's suppose this is a node set B. So then this node cannot be in set B. Okay, this node cannot be in set B. So this node has to have set A. Similarly, this node cannot be in set B. This has to have set A. This node cannot be in set B. This has to have set A. This node, this node cannot be in set B. Sorry, this node cannot be in set A because it has an edge from 2 set A nodes. So this has to be in B. Similarly, this has to be in A, and this has to be in B. This has to be in A. This has to be in A. Okay. So basically, a graph is called bipartite if you can separate the nodes in this graph into 2 sets, such that there is no edge within the set itself. Are you able to understand what I'm saying? If let's say this is the graph, let's say this is the entire graph. Okay, this thing entirely is the graph. So you can say that, okay, I will put this node into set 1, I will put this node into set 1, I will put this node into set 2, I'll put this node into set 2, set 2, set 1, and set 1. So this is a bipartite graph. But if you look at a graph like this, can you separate these edges into 2 sets? Like if let's say this is set, this is node, this is into set 1, then this has to be in set 2. This has to be in set 2, right? And this one, if you, I mean, if you were to look at these two nodes, both of them cannot be in set 1 and both of them cannot be in set 2. Right? If this was 2, then this would not work. If this was 1, then this is fine. But then this has to be either 1 or 2. So both of them would not work. Right? So a bipartite graph is like, a graph wherein you can separate the nodes into two components such that there is no edge between, within the component itself. Right? And the only, like I will just put the statement here. If it doesn't contain an odd length cycle. Okay, if a graph doesn't contain odd length cycle, then the graph can be converted into, can be split into two sets, such that, every node, any set doesn't have an edge within itself. Otherwise, if you have, this is very, obvious. Like if you have a set, sorry, if you have a graph which contains an odd length cycle, let's say this is the entire graph. This contains an odd length cycle. Like let's suppose something like this. Right? Do you think this would work? Like, like if this is 1, then this has to be 2. But then if you look at this node, like you cannot either assign a 1 or a 2 here. So a graph is bipartite if it doesn't contain an odd length cycle. Now my question to all of you is that is a tree a bipartite graph? A tree. The answer is yes. So basically, if you look at a tree, it doesn't contain any odd length cycle, right? So it becomes very obvious. See, if you look at a tree, do one thing. For this entire level, you assign it to node 1. For this entire level, you assign it to node 2. For this entire level, you assign it to node 1. For this entire level, you assign it to node 2. So basically, you keep going down. And if you do something like this, any two, like if you look at any component, it will never have an edge within itself. Right? So a tree is always bipartite. And obviously, any graph which doesn't contain a cycle will be bipartite. But a graph which contains an odd length cycle will not be bipartite. So now tell me one thing, if you have to basically check if a graph has, if a graph is bipartite, what would you do? Would you check for an odd length cycle, or is there some other way which you can do? Because checking whether there exists an odd length cycle is like a bit of a difficult task. Right? Does this sound easy to you? Like, checking an odd length cycle. Checking a cycle seems fine, but checking an odd length cycle, does that seem easy to you? Not so much to me. Union find could work. Union find we haven't discussed right now. Yeah, checking for an odd length cycle would require some extra work. But tell me one thing, how about I start doing something like this? That, I start, my DFS from any random node in the graph. Let's say I mark it node 1. Okay. And then I look at all of its neighbors. I mark them 2. I look at all the neighbors for this node. I look at all the neighbors. I mark them 1. I look at all the neighbors for this node. I mark them 1. And similarly, like, just doing a DFS can tell me whether a graph is bipartite or not. Yeah, just doing a normal DFS and assigning colors. We can assign color black and white, for example. So do you want to see the code for this? And again, now tell me one thing, if you have to check whether there exists an odd length cycle in a graph, can you do it by just checking whether the graph is bipartite or not? This simple DFS algorithm that I'm telling you, you start from a random node, assign it some random color, like 1 or 2, move to other node, all of its neighbors, assign it a different color, move to all of their neighbors, assign them a different color. If you do something like this seems like a very easy algorithm. So using this, you can even detect whether there exists an odd length cycle in the graph or not. You don't have to necessarily find whether there exists an odd length cycle, but just checking whether the graph is bipartite or not. If it is not bipartite, it clearly means there is a cycle of odd lengths. Right? So yeah, let's try to code it. Not very difficult, again, simple stuff. Yeah. So you can use again, have visited and also, have a color, vector int colors. Let's assign them all 0. So 0 is not a color, and 1 and 2 will be the colors black and white. So what you do is you start from, okay, tell me one thing. Do you only need to do a DFS from one node, or do you need to do a DFS from all nodes? Like the graph can be disconnected as well, right? So just take this as a, as a convention that when the graph is disconnected, then it makes sense to do a DFS for all nodes. Okay. If you have to assign a property to every node. And you can just say that, like send I enters with state colors. Okay. Do you need visited here or not? Can you do it without visited array? Because see, a node would be unvisited if it doesn't have a color. As simple as that. So just checking whether a node is visited or not can be directly checked if it has a color or not, right? So yeah, you can remove this. And if we have to assign a random color, then we can just say color of. Now to check if a node is visited or not, we'll just check if color of I equals to 0. We'll say, okay, color of I is 0. So assign it any random color. Let's, like, we can even do something like rand of 1, 2, or we can just say 1. 1 is a random color. No, we don't need this visited anymore. So it's not required. If not visit, if color of E equals to 0, then you do a DFS. Else you say, okay, if color of E equals to color of current, what do you do in this case? If the color of your like if a node has already been visited, but if it has the same color as you, what do you conclude from this? You say C out, not a bipartite graph. Else you say color of E equals to basically assigning a different color than what the current node has. Okay, clear to all of you how you can check whether a graph is bipartite or not. And you can just debug colors. Start and end are not required now. So DFS color.
डिक्लेरेशन ऑफ कलर्स वेक्टर स्पेलिंग एस नहीं रहता वहां पे
हाँ got it. अच्छा एक सेकंड color of I colors होगा यहाँ पे color ही कर देते हैं okay very good. If color of E equals to 0, okay, we also have to assign the color here, right? If it is already having a different color and it is already visible, then we don't need to do anything. So what are the colors that we're getting? For node 1, if you look at it, for node this 0, you are getting color 1. For this, you get color 2. For this, you get color 1. For this, you get color 2. For this, you get color 1. And for this, you get color 2. Okay. Let's try to make an odd length cycle and see if you're getting the same thing. 6,7, let's say. And let's say there is an edge from 4 to 2. So that would make an odd length cycle. Okay, we also have to have this 7. Number of nodes are 7 now. So yeah, we're getting not bipartite. Okay. Is it clear to all of you how this is working? Bipartite, not bipartite. I also have a problem, and I mean, I just think that it's very easy and it can be done without me actually discussing it. So let me just show you, like, this is already there in the slides. So this is like a very easy 1300 level problem, but it uses bipartite graphs. Okay, so you can just solve this problem as a homework. Fine, because this class has already been pretty long, and yeah, I think we've discussed pretty much everything that needs to be discussed in terms of starting graphs. And now for this week, you would mostly be getting questions on properties, bipartite graphs, cycle detection, path construction, all of these things. Starting from next week, we'll have proper algorithms. Like we'll start with shortest path algorithms, then we'll discuss union find, then we'll discuss minimum spanning tree problems and all of these things. So there are pretty interesting problems when it comes to shortest path and MSTs. And mostly the difficult graph problems are based on shortest path and MSTs, not the basic stuff. This basic stuff would be reused up until I would say 1800 level problems or like 1700 level problems. Is topo sort? Yes. Also, like directed graphs are in syllabus. Topo sort, topological sorting is there. Then strongly connected components is there. Then detecting cycles in directed graphs is there. Like today we discussed detecting cycle in an undirected graph, right? So directed graphs or digraphs are a completely different topic. That will be there in third week. And what else? What else will be there? DP on graphs as well. Like when you do topological sorting, then it becomes like a tree only. So you can do DP on trees or DP on graphs then. Somebody saying, could you please tell on what topic of graph is mostly asked in? Mostly, I think it's like MST is shortest path and union find as well, and then like properties, basic properties. I don't think a lot of companies ask basic property problems. They would require some algorithm to be solved. But on code forces, a lot of problems are based on topic main properties as well. Oh, okay. I mean, you're saying it was a tree problem, not a graph problem. Okay. Yeah, because for graph, I think, as far as I remember, in order to find out, the shortest path in a DFS, using DFS, it's not a polynomial time problem. You will have to consider all the paths, and all the paths in a graph are not polynomial at all. They're exponential. Okay. So just give me another second here. So I hope this class was interesting. Please fill up this feedback form. Again, not a lot of you do, but since you already have 6 people, just 6 people right now in the class. So yeah, I would expect at least 5-6 entries in the feedback form. Okay, cool. So let me stop the recording.